In most years, the inner regions of our solar system play host to only a small number of comets. However, late 2025 is proving to be anything but ordinary. 7 major celestial objects are plunging toward the sun simultaneously, including the interstellar giant 3I/Atlas, which continues to expand with each passing day. Astronomers worldwide are charting this extraordinary convergence, an event unprecedented in the era of modern telescopic observation, as these cosmic wanderers hurtle past Earth and the Sun within a compressed 6-month time frame. Some scientists speculate that this unusual concentration of cometary activity might even trigger heightened solar storm activity, while at least one of these visitors could become bright enough to observe with the unaided eye. But what cosmic coincidence has brought so many comets together at once? And what combination of danger and wonder might the celestial traffic jam deliver? Let's explore the most extraordinary comet calendar of our generation. 7 major comets crowding into the inner solar system during a single season represents something almost without precedent. In typical years, astronomers might observe 1 or 2 bright comets passing close enough for detailed study, perhaps 3 if surveys prove particularly fortunate. But a year featuring 7 comets, all diving sunward within mere months, constitutes a kind of phenomenon that stands out even across a century of astronomical records. Since the inception of systematic sky surveys, including Pan-STARRS, Linear, and the Atlas Project, no observing season has witnessed this density of cometary traffic. The last time comet counts even approached these numbers, astronomers were still capturing images on glass photographic plates, and most discoveries occurred through chance encounters or informal communication networks. What makes this convergence truly remarkable isn't merely the total count. This swarm differs fundamentally because it doesn't represent a gradual trickle spread across years. Instead, it's a concentrated surge, with each object threading to the inner solar system in rapid succession. Some arrive from the most distant reaches of space. Others are periodic visitors making scheduled returns. And one, 3I/Atlas, originates from beyond our solar system entirely. That interstellar outlier alone would dominate astronomical headlines in any typical year. Combined with 6 other substantial comets, however, the probability of such an alignment becomes almost infinitesimally small. Statistically speaking, the average year since 2000 has produced just 1 comet reaching naked eye visibility, accompanied by 2 or 3 fainter objects visible only through binoculars or telescopes. Many years pass with nothing but dim, distant fuzzy patches. Even during so-called comet showers, brief intervals when several objects happen to arrive together, numbers approaching 7 are virtually absent from modern astronomical records. According to publicly available logs from the Minor Planet Center, no season since the digital era commenced has hosted more than 4 major comets with perihelion, closest approach to the Sun, inside 2 astronomical units. And that figure doesn't even account for the ecliptic alignment this particular group is displaying. For context, comet discoveries have skyrocketed in recent decades as robotic sky surveys have swept the heavens with increasing thoroughness. Yet the vast majority of detected objects prove to be dim, distant, or short-lived. Bright, accessible comets remain exceptionally rare. The 2025 influx is so statistically anomalous that several astronomers have characterized it as an outlier event, the kind of occurrence that might manifest only once across many human generations. That's precisely why this transcends being merely a list of celestial objects. It represents a phenomenon in its own right, a genuine swarm that challenges our expectations of the solar system's typical rhythms. With so many icy visitors arriving nearly simultaneously, astronomers are approaching this as a single, multi-act spectacle. Focus has shifted from examining individual comets to tracking their collective choreography, how their orbits, alignments, and solar encounters might interact or overlap. It's this rare convergence that's generating both scientific excitement and widespread public anticipation. Before delving into the technical details of perihelion, superior conjunction, and ecliptic alignment, it's worth emphasizing just how exceptional it is to witness 7 major comets sharing the celestial stage simultaneously. C/2022 N2 Pan-STARRS inaugurates the 2025 comet season, reaching perihelion on July 31st at 3.82 astronomical units from the Sun. Its distant trajectory keeps it well beyond Mars, where sunlight grows thin, and only the most sensitive telescopes can monitor its progress. Pan-STARRS establishes the outer boundary for the swarm, a quiet prelude before more dramatic arrivals commence. C/2025 R2 Swan follows close behind. Discovered on September 11th and racing toward perihelion just 1 day later on September 12th at 0.50 astronomical units. Swan's highlight arrives on October 21st, when it sweeps past Earth at merely 0.25 astronomical units, approximately 37 million kilometers. This close encounter makes it a prime candidate for observation, particularly in the pre-dawn sky across the northern hemisphere. Swan's rapid motion and favorable geometry offer a rare opportunity to study a comet's interaction with both the Sun and Earth in real time. 414p/stereo will swing around the Sun on September 27th with a perihelion distance of 0.52 astronomical units. Its orbit dips below the ecliptic plane, making it challenging for ground-based telescopes and frequently lost in solar glare. This comet, which shares its name with the Stereo spacecraft mission, proves better suited for space-based imaging. Its low trajectory provides a different vantage point for solar studies. C/2025 K1 Atlas arrives next, reaching perihelion on October 8th at just 0.33 astronomical units, closer to the Sun than Mercury ever ventures during its orbit. This tight solar passage means Atlas will undergo rapid transformations, making a key subject for monitoring sudden outbursts and tail development. Its proximity to the Sun places it squarely at the heart of the swarm's most intense activity. 3I/Atlas, the interstellar visitor, will reach Superior Conjunction on October 21st, passing behind the Sun from Earth's perspective. Perihelion follows on October 29th at 1.36 astronomical units, just inside Mars' orbital path. With an orbital inclination of approximately 5 degrees, 3I/Atlas tracks close to the ecliptic plane, sharing the sky with planets and fellow comets. For several days, both 3I/Atlas and Swan will occupy critical positions for solar interaction research, though neither will be easily visible from Earth's surface. C/2025 A6 Lemon peaks at perihelion on November 8th at 0.53 astronomical units. Its trajectory keeps it visible in the evening sky after sunset, offering one of the most accessible observing windows of the entire group. Current forecasts suggest it could reach magnitude 4 or possibly even 3.5, potentially visible to the naked eye for northern observers during early November. 240p/NEAT completes the sequence, reaching perihelion on December 19th at 2.12 astronomical units. As a periodic comet, it's fainter and more distant, but its presence underscores the crowded state of the inner solar system by year's end. Each comet's orbital path, perihelion date, and relationship to the ecliptic plane creates a tightly packed calendar, setting the stage for the dramatic solar interactions that follow. Comet tails are far more than cosmic streamers trailing through space. They're living records of invisible forces constantly at work throughout the solar system. When a comet approaches the Sun, intense solar radiation heats its nucleus, releasing gas and dust that form two distinct tails, a broad, pale dust tail and a narrow, electric blue ion tail. The ion tail, in particular, provides a direct connection to the Sun's magnetic field. It consists of charged particles swept away by the solar wind, an unceasing torrent of plasma and magnetic fields that spirals outward from the Sun at hundreds of kilometers per second. But the ion tail isn't a permanent structure. It can be severed in an instant, a phenomenon known as a tail disconnection event. The physics underlying this dramatic occurrence is rooted in magnetic reconnection. As a comet moves through the solar wind, it sometimes encounters abrupt changes in the interplanetary magnetic field, such as a coronal mass ejection, CME, or a crossing of the heliospheric current sheet. These are not gentle transitions. The magnetic field can rotate by 90 degrees or more within minutes. When that happens, the comet's plasma environment cannot adjust quickly enough. The old tail is cut loose, drifting off into space, while a new tail begins forming, perfectly aligned with the new direction of the solar wind. One of the most spectacular examples was captured in April 2007, when the Stereo spacecraft observed a CME slam into Comet Encke. The ion tail was severed cleanly, with a visible gap forming near the nucleus and the detached tail floating away, a textbook case that matched magnetohydrodynamic simulations almost frame by frame. These events aren't rare during solar maximum. With several comets diving near the ecliptic in late 2025, the probability of capturing a live disconnection event is higher than ever. The dust tail, by contrast, is less affected by these magnetic storms. It's governed by sunlight pressure and gravity, not magnetism. Only the most powerful CMEs can reshape or truncate a dust tail, usually by stripping away part of the coma, the cloud of gas around the nucleus, or redirecting the outflow. For most observers, the ion tail sudden breaks and regrowth are the signature to watch, a direct manifestation of the sun's restless energy, written across millions of kilometers of space. Solar physicists are monitoring this comet swarm with a mixture of anticipation and concern, and not merely for the visual spectacle. Behind the scenes, an intense debate is unfolding over what these close passages might mean for the sun's behavior. Some research groups, particularly the NASA Community Coordinated Modeling Center, CCMC, team, argue that the sudden influx of cometary plasma and dust, especially from ecliptic-aligned comets, could actually nudge the sun toward more frequent or intense outbursts. Their computer simulations demonstrate that when a dense, active comet crosses a heliospheric current sheet or passes through a coronal mass ejection, the magnetic geometry can shift rapidly, sometimes triggering a classic tail disconnection event. In these models, the sun's magnetic field lines drape around the comet, and if a CME sweeps through precisely the right angle, the ion tail snaps off, sometimes within minutes. The CCMC's magnetohydrodynamic, MHD, simulation suggests that with several comets in play, especially during solar maximum, the odds of witnessing multiple dramatic tail severances increase substantially. Some models even propose that the excess plasma might help seed new instabilities in the solar wind itself. However, not everyone is convinced. The Solar Orbiter and Parker Solar Probe teams point to their own in situ data, arguing that most tail disruptions are far more subtle than the models predict. They've cataloged numerous minor kinks and bends in comet tails that never escalate into full-scale disconnections, even during strong CME events. Their direct field measurements reveal that small-scale turbulence, micro-reconnection events, and the background variability of the solar wind can all play significant roles, sometimes more so than the headline-grabbing CMEs. From their perspective, the sun's own magnetic cycles and large-scale field reversals are the true drivers, with comets acting more as passive tracers than active agents. They caution against overestimating potential risks to satellites or electrical power grids, noting that even during the dramatic 2007 Enki event, the operational impact was negligible. Still, with CME rates expected to reach 2 to 5 per week during the late 2025 solar maximum, both camps agree on one crucial point. This represents a rare opportunity to test their theories in real time. Space weather officials are ramping up monitoring efforts, and citizen scientists worldwide are preparing for a global observation campaign. If a major tail disconnection occurs while a comet is favorably positioned, observers ranging from backyard telescopes to orbiting spacecraft will be ready to capture it. For now, the debate has sharpened everyone's focus. Every new CME, every unusual twist in a comet's tail, could tip the scales in this ongoing scientific standoff. When astronomers first calculated the orbit of 3I/Atlas, the numbers didn't fit any pattern characteristic of native solar system comets. Its trajectory is hyperbolic, with an eccentricity well above 1, meaning it's not merely visiting, it's passing through our solar system, never to return. That distinction alone sets it dramatically apart. Only 2 other objects, Oumuamua in 2017 and Borisov in 2019, have ever been confirmed as interstellar before it. But Atlas differs in more ways than its origin. Early measurements from the Hubble Space Telescope and James Webb Space Telescope suggest a nucleus somewhere between 320 meters and 5.6 kilometers across, a significant uncertainty range. Yet the coma, that halo of gas and dust it's shedding as it approaches the sun, has already expanded to approximately 700,000 kilometers wide. That's nearly the diameter of Jupiter, and it continues growing by the week. Unlike most comets, which spend eons locked in the outer reaches of our solar system before making a single pass near the sun, Atlas originates from much farther away. It was likely ejected from another star system entirely, carrying material forged in a different cosmic neighborhood altogether. Its composition proves equally distinctive. Spectroscopic analysis reveals a coma dominated by carbon dioxide and other volatile gases, with water vapor surprisingly scarce and cyanide detectable only in faint traces. These are chemical signatures rarely observed in such abundance among local comets. The object's motion is equally telling. It entered the solar system at a steep angle, skimming the ecliptic plane by only about 5 degrees, with a velocity that leaves no doubt regarding its foreign origin. The scientific value is enormous. Each observation offers a chance to compare the building blocks of distant planetary systems with our own. And there's more at stake than chemistry alone. As Atlas rounds the sun, it leaves behind a trail of dust and debris that Earth may intersect in 2026, a rare opportunity for planetary defense teams to monitor interstellar material up close, studying its composition, structure, and potential impact characteristics. The story of 3I/Atlas is still unfolding, but even at this early stage, it's rewriting our understanding of the boundaries and nature of our solar system. From late October through early November 2025, the sky opens a rare window for comet enthusiasts. No advanced equipment is required, just clear skies, proper timing, and perhaps a bit of patience. The show begins before dawn on October 21st, when C/2025 R2 Swan makes its closest approach to Earth, sweeping by approximately 0.25 astronomical units. Even through modest binoculars, Swan's tail will stretch across an impressive 2.5 degrees, 5 times the apparent width of the full moon. Its head glows at magnitude 6 to 7, faint but within reach for anyone willing to rise early and scan the southeastern sky. For most northern latitudes, Swan climbs to nearly 40 degrees above the horizon at civil twilight, making it an ideal pre-dawn target. Meanwhile, 3I/Atlas will slip behind the sun at Superior Conjunction. While ground-based telescopes lose sight of it, the action shifts online. Solar observatories like Seoul's LASCO C3 coronagraph maintain constant watch, capturing both 3I/Atlas and, at times, Swan as faint moving points against the sun's outer atmosphere. These real-time data feeds are publicly accessible. Anyone can join the hunt for sudden changes, outbursts, or even a tail disconnection event triggered by a solar storm. By early November, C/2025 A6 Lemon will steal the spotlight in the evening sky. Current forecasts place its brightness at magnitude 4, possibly reaching 3.5. Bright enough to spot with the naked eye from dark sky sites, especially for viewers across the northern hemisphere. Lemon sits low in the southwestern sky after sunset, its coma and tail brightening each night as it approaches perihelion on November 8th. For many observers, this will represent the easiest comet to see in years. Whether you're using binoculars, a backyard telescope, or simply your own eyes, this season offers a compelling reason to step outside and witness the solar system in motion. The optimal observing nights are October 21st for Swan's closest approach and November 6th through 12th for Lemon's prime viewing period. For comets hiding near the sun, the world's coronagraphs serve as your window, just a browser click away. Forecasting comet brightness is a lesson in scientific humility. Regardless of how much data astronomers collect, brightness predictions can swing by as much as 2 magnitudes each year, sometimes even more. A comet expected to blaze at magnitude 3 can fizzle to magnitude 5 or 6, while a faint, overlooked newcomer can suddenly erupt, outshining all expectations. These surprises stem from factors no model can fully pin down: grain size distribution in the dust, the precise mixture of ices, how deeply sunlight penetrates a crust that might be meters thick. Even with the most sophisticated thermophysical models, a slight shift in solar heating patterns or a hidden fracture can transform the story overnight. For 3I/Atlas, the uncertainties run even deeper. Its nucleus could be as small as 320 meters or as large as 5 kilometers. Current Hubble and JWST observations bracket this range, but the true size remains elusive. The coma's dominance by carbon dioxide is clear from spectroscopic data, yet the complete inventory of volatiles and dust remains tantalizingly out of reach. without strong detections of water vapor or other familiar gases. Each new dataset reshapes working theories. The only certainty is that forecasts will continue evolving right up to and beyond perihelion. Looking ahead, the next generation of sky surveys, particularly the Vera C. Rubin Observatory's Legacy Survey of Space and Time (LSST), promises to catch more of these unpredictable objects. Routine, all-sky imaging would detect faint, fast-moving objects that today might slip through unnoticed. But even in the LSST era, the science will be shaped as much by what we don't see coming as by what models predict. For now, the best advice is to watch the sky with an open mind and expect the unexpected. The 2025 comet swarm represents more than an astronomical curiosity. It's a convergence of celestial mechanics, plasma physics, and observational opportunity that may not repeat for generations. 7 major comets threading through the inner solar system within months, including an interstellar visitor with a carbon dioxide coma measuring over 700,000 kilometers wide, creates an unprecedented laboratory for studying comet behavior and solar interactions. As researchers continue monitoring these objects, the 2025 swarm will test and expand our understanding of cometary dynamics, solar wind physics, and the nature of interstellar material. It's adding a remarkable new chapter to the ongoing story of our solar system, one written in ion tails, magnetic reconnections, and the patient observations of astronomers worldwide. The show is just beginning. Don't miss it. At 4:47 Universal Time Coordinated on October 21st, amateur astronomer Maria Chun in New Mexico noticed something unusual while imaging Swan through her 8-inch telescope. The comet's ion tail, which had been streaming steadily for days, suddenly showed a strange kink near the nucleus. Within minutes, her social media post had caught the attention of professional observatories worldwide. What happened next would become one of the most documented celestial events in history. At 5:12 Universal Time Coordinated, NASA's Solar Dynamics Observatory detected a powerful X2.7 class solar flare erupting from active region AR 3847. The associated coronal mass ejection was enormous, traveling at nearly 2,000 kilometers per second and aimed directly at the inner solar system. But this wasn't just any CME. Its trajectory placed it on a collision course with not one, but 3 comets, Swan, 3I/Atlas, and C/2025 K1 Atlas, all positioned within a 45-degree arc of sun. The race was on. Would the CME reach the comets before they moved out of alignment? How would the interstellar visitor react compared to its solar-born companions? Every major telescope network on Earth and in orbit began coordinating in real time. 18 hours after the flare, at 23:34 Universal Time Coordinated, Swan took the first hit. The Stereo A spacecraft, positioned perfectly to observe the event, captured the moment in stunning detail. The CME's magnetic field slammed into Swan's plasma environment like a cosmic guillotine. The ion tail, that brilliant blue streamer stretching 2.5 degrees across the sky, severed completely in less than 4 minutes. Amateur observers watching from darkened fields across North America witnessed something they would remember for the rest of their lives. The tail didn't just disappear. It seemed to unravel, fragmenting into ghostly wisps that slowly faded against the stars. Meanwhile, near the nucleus, a new tail began forming almost immediately, growing at a visible rate, pointing in an entirely different direction as it aligned with the new magnetic field orientation. Social media exploded. Within an hour, #CometSwan was trending globally, with thousands of images and videos flooding in from observers on 6 continents. But the astronomical community knew this was only the beginning. 36 hours after the initial flare, the CME reached 3I/Atlas. Scientists at the European Space Agency's Solar Orbiter mission had positioned the spacecraft to capture this historic moment, the first time humanity would witness an interstellar object interacting with a major solar storm. What they observed defied all predictions. Instead of a clean disconnection like Swan, 3I/Atlas responded with a violent outburst. The coma, already massive at 700,000 kilometers, suddenly expanded by another 200,000 kilometers in just 6 hours. New spectral lines appeared that hadn't been detected before, complex organic molecules being ripped from a nucleus by the solar onslaught. Most surprisingly, the comet briefly brightened by nearly 2 magnitudes, becoming visible in Soho's coronagraph as a distinct, glowing point. The chemistry we're seeing is completely alien to solar system comets, Dr. Sarah Rothstein of the JWST team announced in an emergency press conference. Whatever star system this thing came from, it formed under very different conditions. We're watching interstellar material being processed by our sun for the first time in recorded history. But the data revealed something even more intriguing. The dust trail left by 3I/Atlas showed an unusual structure, periodic clump space at regular intervals, suggesting the nucleus might be fragmenting or had an irregular rotation. More concerning, trajectory refinements indicated Earth would pass directly through this debris trail in late March 2026, potentially producing an unprecedented meteor shower of interstellar origin. On October 23rd, as astronomers were still analyzing the 3I/Atlas data, something extraordinary appeared in the LASCO C3 coronagraph images. Due to the peculiar orbital alignments, all 3 comets that had been struck by the CME, SWAN, 3I/Atlas, and C/2025 K1 Atlas momentarily appeared in the same field of view, along with Venus and Mercury. It was alignment that had never been photographed before. 2 planets and 3 comets, one from another star system, all visible simultaneously against the sun's corona, their tails pointing in different directions like cosmic compass needles, mapping the solar wind's complex structure. Professional observatories weren't the only ones capturing this moment. The image was accessible to anyone with an internet connection. Classrooms around the world tuned in. The feed crashed multiple times due to overwhelming traffic. NASA servers struggled under the load as millions watched live, witnessing the solar system's most remarkable celestial gathering in modern times. While the world focused on the drama near the sun, C/2025 A6 Lemon was quietly approaching its November 8 perihelion in the evening sky. But Lemon had a surprise in store. On November 5th, amateur observer Roberto Dias in Brazil noticed Lemon had suddenly brightened, not gradually, but dramatically, jumping from magnitude 4.1 to 2.8 in less than 12 hours. The comet had experienced a massive outburst, likely triggered by a fresh section of ice being exposed to sunlight as it approached perihelion. For 3 glorious nights, from November 6th through 8th, Lemon blazed in the southwestern sky, easily visible to the naked eye even from moderately light-polluted suburbs. Its tail stretched nearly 5 degrees, 10 times the width of full moon, creating a spectacular sight that captivated millions of viewers who had never seen a bright comet before. Social media platforms filled with photos, families posing with Lemon in the background, children seeing their first comet, proposals made under its celestial glow. News outlets that typically ignored astronomical events ran front-page stories. For many people, Lemon's unexpected performance became the defining celestial moment of 2025. As November progressed and the swarm began to disperse, scientists started compiling what would become the most comprehensive data set ever collected on multiple comets during a solar maximum. The results were staggering. The NASA CCMC modeling team had been partially vindicated. The CME did trigger dramatic tail disconnections, and the excess cometary plasma had measurably affected local solar wind parameters. However, the Parker Solar Probe data revealed something neither camp had predicted: microscale magnetic reconnection events occurring constantly in the comet's plasma environments, creating a turbulent wake that persisted for millions of kilometers. The debate hadn't been settled. It had evolved. Both teams now had evidence supporting their positions, suggesting that comet-solar interactions operated on multiple scales simultaneously, each important in different ways. For 3I/Atlas specifically, the data was transformative. Analysis of its unusual chemistry suggested it formed in a planetary system around a carbon-rich star, possibly an older system with different metallicity than our own. The organic molecules detected during the outburst included several that had never been observed in space before, opening new questions about the diversity of planetary formation across the galaxy. As 2025 gave way to 2026, astronomers refined their predictions for Earth's March passage through 3I/Atlas's debris trail. The calculations were concerning. If the fragmentation they'd observed was real, Earth could encounter a dense stream of interstellar particles. potentially the most active meteor shower in decades or possibly a non-event. Nobody knew for certain. Meteor networks worldwide prepared for March 23rd, when Earth would cross the debris trail's predicted center. Researchers coordinated with the International Space Station, commercial satellite operators, and amateur astronomy groups to monitor the event from every possible angle. When the night arrived, the results exceeded even optimistic predictions. Beginning at 2:15 Universal Time Coordinated, meteors started appearing at a rate of 400 per hour at peak. Not the thousands some had feared, but far more than any regular annual shower. But these weren't ordinary meteors. They were different. Many burned with unusual colors, deep purples and strange oranges never seen in typical meteors, caused by their alien chemistry. Spectroscopic analysis revealed the same organic compounds detected by JWST months earlier. They were vaporizing fragments of another world from another star burning in Earth's atmosphere. Some pieces were large enough to trigger cameras on all-sky fireball networks. A few potentially meteorite-producing fireballs were tracked, and the race began to find fragments, actual pieces of material from another stellar system that had survived atmospheric entry. By dawn, 2 possible meteorites had been recovered, one in Montana, another in Kazakhstan. If confirmed, they would be the first interstellar meteorites ever found. Physical samples from beyond our solar system, delivered courtesy of the Great Comet Swarm of 2025. The 2025 comet swarm lasted 6 months, but its impact will resonate for generations. It proved that the solar system could still surprise us, that rare events do happen, and that when they do, they cascade in unexpected ways. Amateur astronomers discovered they could contribute to cutting-edge science, capturing crucial data during moments when professional telescopes were pointed elsewhere. Millions of people who had never paid attention to astronomy found themselves checking sky maps and setting alarms to wake before dawn. Children who witnessed Lemon's outburst or the March meteor shower might become the next generation of planetary scientists. For researchers, the swarm provided answers to questions that had lingered for decades, while simultaneously opening entirely new areas of investigation. The debate over comet-solar interactions had evolved into a more sophisticated understanding. The chemistry of 3I/Atlas was still being analyzed, with new papers appearing weekly. And hanging over everything was a tantalizing possibility that somewhere in Montana or Kazakhstan, locked inside a small, dark stone, might be secrets from another star, answers to questions we hadn't yet learned to ask. As 2026 progresses, astronomers continue monitoring the inner solar system, now returned to its normal, quieter state. The 7 comets of 2025 have dispersed, some retreating to the outer solar system. Others, like 3I/Atlas, leaving forever, carry with them Earth's radio signals and the record of their brief passage through our cosmic neighborhood. But the Vera Rubin Observatory has begun operations, and its powerful survey is already detecting faint comets that previous generations of telescopes would have missed. Preliminary counts suggest that the 2025 swarm, while unprecedented in modern times, might not be as rare as initially thought when viewed across longer timescales. Perhaps every few centuries, the solar system experiences these cosmic convergences. We've simply never had the tools to properly observe them until now. The question now isn't whether another great swarm will come, but when, and whether we'll be ready to witness it with even more sophisticated instruments, deeper understanding, and perhaps, if we're very lucky, another messenger from the stars. Until then, we have the images, the data, the recovered meteorites, and the memories of that extraordinary season when 7 comets danced through our solar system and the sky itself became a classroom, teaching us once again that we live in a universe far stranger and more wonderful than we dare imagine. The Great Comet Swarm of 2025 has passed into history. But the universe is vast, and it's only a matter of time before the next cosmic surprise arrives. Keep watching the skies.